There's your thought for the day, by Teddy Roosevelt. What position did Teddy Roosevelt hold? Yes?
President?
Yes, he was a president. So, anyway. So Section 8.2 is slope. Our objectives for 8.2 is to use slope to identify quadrilaterals and prove the product of perpendicular slopes is -1. So some background on slope. Given the coordinates of 2 points to determine a non-vertical line, the slope m of the line is the ratio of the change in y, which is the up and down distance, and the change in x, which is the horizontal distance, right to left. So slope of PQ equals y2 minus y1 over x2 minus x1. The difference, y2 minus y1, is called the rise, and x2 minus x1 is called the run of PQ. Thus, we could also define the slope of a non-vertical line to be the ratio of its rise to run. Notice we can write the slope of PQ as y1 minus y2 over x1 minus x2, because those, whether you use the y2, x2 first or second, you're going to get the same result. The slope of a line segment PQ is the slope of line PQ. If line PQ is vertical, then x1 equals x2. And the denominator of the slope, by definition, namely x2 minus x1, is 0. Therefore, we say a vertical line slope is undefined because you cannot divide by 0. Alright, if it's straight up and down, your x2 and x1 are going to be the same thing. So that would be 0. You can't divide by 0, so we say a vertical line has undefined slope. Any questions there? Okay? Find the slope of each line segments with the given points. Okay. So if we find the slope of AB, slope of AB is equal to, okay, so the y values are both 4, so it would be 4 minus 4 over -5 minus the -1. Which is equal to 0 over -4, which equals to 0. The slope of AB is 0. So horizontal line is going to have a 0 slope. Okay, let's do one that's not vertical or horizontal. Let's do CD. We're going to let the point C and C be x2 and y2. So we have m of CD is equal to 5 minus 2 over 1 minus 3, which is equal to -3 over 2. -3/2. Go ahead and find the slope of EF and GH on your own. Find EF and GH on your own. Okay, what'd you get for the slope of VF? Shatiz.
For the slope of EF, I got 1.
Right. Slope of VF equals 1. Anybody need to see that? Lexi, what'd you get for the slope of GH? Yeah, GH is undefined. It's a vertical line. It's undefined because it's vertical. All right, any questions there? All right. So there's a summary of the different slopes. Horizontal is 0, vertical is undefined, and we got positive and negative slope. All right. Example 8.9. An experiment yielded the data points graphed in the figure. Determine whether the 3 points are collinear. How could we tell if these 3 points are collinear? Yes?
If they have the same slope.
Right. So if we have, let's label them A, B, and C. If we find the slope of AB, and if that slope is the same as the slope of BC, this should be over the AB, not over the M. If that's the same as the slope of BC, then the points should be collinear. So go ahead and find those slopes. Go ahead and figure out those slopes, see if they're collinear. All right, so what did you determine? Is the line collinear?
They're not.
They're not? Okay, you should have gotten 0.042 for each slope.
0.042?
Yep. They might get 0.042?
I did it the other way around. That's why.
All right. Should get the same result whether you do, whichever point you do first. You just have to be consistent. Slopes of parallel and perpendicular lines. Because slope is a measure of the inclination of a line with respect to horizontal, two non-vertical parallel lines must have the same slope. Also, vertical lines are parallel. The next theorem summarizes these relationships. Two lines in the coordinate plane are parallel if and only if their slopes are equal or their slopes are undefined. For the quadrilateral ABCD with A equal to -2, 5 and B 6, 3 and C 8, -2 and D 0, 0, use slopes to verify the ABCD is a parallelogram, and then we have to verify that the diagonals of ABCD bisect each other. Alright, so to verify that ABCD is a parallelogram, what do I have to show has the same slope? Which segments? Yes. Opposite sides. So draw yourself a picture so you can sort of visualize it. We've got A, B, C, D. Okay. So the measure of AB should be the same as the slope of AB should be the slope of same as the slope of CD. Let's see. Plug in. So we have 3 minus 5 over 6 minus a -2. That equals -2 over 8, which is -1/4. Right? That's the slope of AB. Let's do the slope of CD. M of CD is equal to -2 minus 0 over 8 minus 0. That equals -1/4. Okay, so AB and CD are parallel. Now let's test to see if BC and DA are parallel. So we do the slope of BC. It's going to be -2 minus 3 over 8 minus 6, which is equal to -5/2. And then we do M of DA. M of DA is equal to 5 minus 0 over -2 minus 0, which is equal to -5/2. Okay, so the opposite sides are parallel. All right, everybody got that? Any questions? Now, how are we going to show that the diagonals bisect each other? How could we show the diagonals bisect each other? Shatiz.
Because an attribute of a parallelogram is that the diagonals bisect each other.
Okay, that's true, but how can we mathematically, how can we prove that? Yes.
We could find the distance of the diagonals and then find the midpoint and then see if the midpoint is the same exact coordinate.
Right, you don't need to find the distance, all you need to do is find their midpoint. Right? Find the midpoint of what? What line? Yeah.
It would be AC and BD.
Yeah, we find the midpoint of AC and the midpoint of BD. And if they have the same midpoint, then we know the diagonals bisect each other. So let's do that. Midpoint of AC is equal to 8 minus 2, or plus a negative 2, so 8 minus 2 over 2, and negative 2 plus 5 over 2. So that is equal to 3 over 2, and not 3 over 2. It is equal to 6 divided by 2 is 3, 3, and 3 over 2. Then we do the midpoint of AC, or BD. Midpoint of BD, 6 plus 0 over 2, and 3 plus 0 over 2. So that's going to equal to 3 and 3/2. Right? So they have the same midpoint. So they bisect. All right. Any questions? Okay, so now we have this figure 820. We have to prove that ABC is has a right angle at C. Then we're going to find the products of the slopes of AC and BC. So how could I, without using the slopes, how could I prove that this is a right triangle? What could I do? Lexi. Correct. So, this is a lot of plug and chug, right? You got to plug normal numbers into formulas and find the distances and it's and slopes, so it's just a lot of algebra work. But she's correct. That's how we do it. So we're going to use Pythagorean theorem. So let's do the distance from A to B. A to B is equal to the square root of, let's see, negative 3. We're using A as our x2 and y2. So it's negative 3 minus 4 squared plus 4 minus 5 squared, so that's going to equal to the square root of 7 squared plus 1, which is equal to radical 50. That's AB. Then we do AC. AC equals to the square root of, we plug in the numbers, negative 3 minus 3 squared plus 4 minus 2 squared, which is equal to the square root of 6 squared plus 2 squared, which is equal to radical 40. Then BC. BC is equal to the square root of 4 minus 3 squared plus 5 minus 2 squared, which is equal to the square root of 1 squared plus 3 squared, which is equal to square root of 10. Alright, so now we do Pythagorean theorem. AC squared plus BC squared equals AB squared. So that would be radical 40 squared plus radical 10 squared equals radical 50 squared. So that's 40 plus 10 equals 50. And that's true, so therefore we have a right triangle. Everybody have it? Okay, now we're going to prove the slopes. We're going to find the product of the slopes of AC and BC. So the product of the slope, so M of BC is equal to 5 minus 2 over 4 minus 3, which is equal to 3 over 1, which is equal to 3. M of AC is equal to 4 minus 2 over negative 3 minus 3, which is equal to 2 over negative 6, which is equal to negative 1/3, right? So then we have M of BC times the slope of AC equals to 3 times negative 1/3, which is equal to 1. Negative 1, sorry, equals negative 1. 3 times negative 1/3 is negative 1. So, we can see that the product of the slopes of two perpendicular lines is negative 1. That's our next theorem. Everybody have that? Okay, so our next theorem is two lines in a coordinate plane are perpendicular if and only if one line is horizontal and the other is vertical. Alright, so if they're horizontal and vertical, we know they're perpendicular, or if the product of their slopes is negative 1. Okay, given two perpendicular lines, L1 and L2, through the origin, neither of which is vertical, prove that the product of their slopes is negative 1. Okay, so how we're going to do this is we're going to put a point on line 1 that is 1 over and M1 up. So the y distance is M1. Then we're going to put a point on the down below, and we're going to have it be coordinate 1 M2. So it's a vertical line. So what I have there is a right triangle. And so we've got the slope. We do the equation. Line 1's equation is going to be y equals, okay, and if we do the slope, it's 1 over M1 up, so that would be rise over, so it'd be M1 times x plus b. There's no y, the y-intercept is 0, so it's just M1 times x. So if x equals 1, then y equals M1. So that's how we get the point. We've got the point 1 M1. And for line 2, we've got y equals M times x, M2 times x. And if x equals 1, then y equals M2. And then we have the point 1 M sub 2. Alright? So we'll come back to that. Now we're going to do the Pythagorean theorem. Everybody have that? So I'm going to clear this out. We're going to do the Pythagorean theorem. So Pythagorean theorem. If we do it between, with those coordinates as shown in the figure C, we've got it's going to be the square root of 1. So we go from the point 1m1 to 0. It's going to be the square root of 1 minus 0 squared plus m1 n sub 1 minus 0 squared, which is equal to plus. That's the distance from. That's this distance, and then we're going to do the second distance is going to be from 0 to the m2, which is going to be plus. So this was squared. Okay, that first quantity, this first distance we found, we're squaring that. Now we're finding this distance right here. That's going to be the square root of 1 plus m sub 2 squared, and that's squared, and that's going to equal the distance from the 2 points, which is the x value doesn't change, so that would be 0, so it's just m1 minus m2 squared, right? So we simplify and we get the square root of 1 plus m sub 1 squared plus, and all that's squared, plus the square root, that's plus the square root of 1 plus m sub 2 squared, all squared, and that's going to equal to, then we're going to do m1 minus m2 squared, so that's going to be m1 minus m2 times m1 minus m2, right? And then we square all that out and we get 1 plus m sub 1 squared plus 1 plus m sub 2 squared equals, we do FOIL, m sub 1 squared minus 2 m1 m2 plus m sub 2 squared. So that's going to be, we simplify both sides and we get 2 equals negative 2 m1 m2, and then we divide by both sides by negative 2, and we get, I'll take it up here to the top, we get m1 times m2 equals negative 1. Alright, so that is a proof of that slopes equal negative 1 when they're perpendicular. Questions? Alright. So we're going to prove the diagonals of a rhombus PQRS in the figure 822 are perpendicular using a coordinate proof. Go ahead and do that on your own. Prove that those diagonals are perpendicular. Okay, so you should have gotten the slope of PR was -1 and the slope of QS was 1. You multiply those two together and the product is -1. And if the product of the slopes is -1, then we know they are perpendicular. Any questions? No questions. Okay, let's see. Then that's all I've got for today. Okay.